It seems like a simple, intuitive idea. If you want a project to go faster, just add more people. And yet, many of us have seen the exact opposite happen. Adding more resources can paradoxically make a system slower and less efficient. In this explainer, we're going to look at the underlying structure that causes this counterintuitive outcome.
So to really get to the bottom of this, we'll start by looking at that core paradox. Then we'll build a very simple model of a system to understand its basic parts. From there, we'll dig into the hidden costs of communication and integration, see how these costs pile up, and finally, pull it all together into a general principle of how systems work.
All right, let's begin with that central conflict between what we expect to happen and what actually happens. Why does a strategy that's meant to speed things up so often end up doing the opposite? Well, the common assumption is pretty straightforward. You add a person, you add a unit of productivity. It should be linear. But the reality that we observe is one of diminishing returns. After a certain point, each new person you add contributes less than the person who came before, and eventually you can even see a net decrease in the system's output. To really understand this phenomenon, we need to strip the system down to its most basic parts. This lets us see the structure itself, independent of any specific industry or situation. The first component is what we'll call the agent. Now, this can represent any individual productive unit inside the system. It could be a person, a team, or really any node that's capable of doing work. And the second component is, of course, the task. This represents the productive work that the system is actually designed to do. The whole goal of the system is for the agents to act on this task. Okay, so now we can introduce the first hidden cost of adding more agents. You see, for agents to actually work together on a shared task, they have to coordinate. And that coordination requires connection. With just 2 agents, the system is incredibly simple. There's only one communication channel needed to keep them aligned. But watch what happens when we add just one more agent. We don't just add one more connection. The number of connections actually triples, going from 1 to 3. Add a 4th agent, and the number of connections doubles again, jumping from 3 to 6. You can see the growth here is not linear at all. By the time we get to 5 agents, the system has to support 10 different communication channels. The complexity has just exploded from where we started with our simple 2-agent system. This effect is known as communication overhead. The number of pathways for communication grows exponentially as you add more agents. So as a system gets bigger, more and more of its resources get diverted from actually doing the task to simply talking about the task. But that's not the only cost. A second, very different cost appears whenever new agents are brought into an existing system. This is the cost of integration, or what's sometimes called ramp-up time. Think about it. Adding a new agent isn't an immediate gain. An experienced agent has to stop their own productive work to train the new person. And during that training period, the system's total output actually goes down for a little while, as one person is teaching and the other isn't productive yet. And this isn't just a theory. A phenomenon observed as the Ringelmann effect shows that as the size of a group increases, the average effort from each individual tends to drop. This is a result of both coordination loss, people literally getting in each other's way, and motivation loss, where any one person's contribution feels less significant. This quote really illustrates a final, critical constraint: task divisibility. Some tasks are just sequential by nature. They can't be sped up by throwing more labor at them. Adding more agents to a task like this doesn't make it finish any sooner, it just drives up the coordination cost. So you have these 2 costs, communication overhead and integration drag, and they both accumulate as a system gets larger. Eventually, the system can hit a tipping point where the cost of adding one more person is actually greater than the value they contribute. In a small, efficient group, you can see that the vast majority of resources are going toward the main task. Coordination is just a minor cost of doing business. But as the group grows, it can hit a point where half of its resources are spent on productive work, and the other half are spent just managing the system itself. This is really that point of diminishing returns. And in a state of what's called diseconomy of scale, the system has become top-heavy. The overhead from coordination and communication is now eating up most of the system's resources, leaving very little for actual work. At this point, adding more people literally makes the system slower. Now, what's crucial to understand is that this slowdown isn't happening because of anyone's mistake or failure. It is an emergent property of the system's structure. We can actually break this down into a simple 3-part principle. First,
As the system scales by adding more agents, the number of connections and dependencies between those agents grows at a much faster, exponential rate.
Second, all of those new dependencies have to be managed. The agents now have to spend effort just to stay synchronized and aligned on the task they're all trying to do. And third, coordination isn't free. It consumes time and energy, resources that can no longer be spent on direct, productive work. This entire phenomenon is captured by what's known as Brooks' Law. What it reveals is that the slowdown we see in growing systems isn't some strange anomaly that needs to be fixed. Instead, it's an inherent structural trade-off between the size of a system and its efficiency. The very act of scaling introduces a cost that can, eventually, overwhelm the benefits of scale itself.